Hello everyone. So far in life on planet Earth, we saw that life can be studied at different scales. We can look at life from the perspective of the biosphere, which is all the ecosystems on Earth. We can look at specific ecosystem or communities within that ecosystem. In communities, we have populations that are basically many individuals that belong to the same species. From the population, we can zoom in organisms, right? One particular organism in that population. From the organism, we now know that we can look at organ systems. From organ systems, the lower level, it's going to be organs. Then the lower level, it's going to be tissues. And from tissues, we have cells making up tissues. And the cells are made up of organelles, which themselves are made up of molecules, right? So from that perspective, the molecules are made up of elements, atoms that come together to form very complex structures. Now, having said this, what are the different elements that make up living organisms? How do they come together to form complex structures? So this is going to be the topic for this chapter. We're going to address the chemistry of life. As word of introduction, we saw that in the human impact on our environment, we have more and more carbon dioxide in the atmosphere. And it is no more secret that this high amount of carbon dioxide in the atmosphere matches human activity in terms of burning fossil fuel and ending up with a large amount of carbon dioxide that actually plays the role of greenhouse gas, causing a global increase in the temperature worldwide. But in addition to that, there is another phenomenon that happens. And in this case, we are going to take a look at how carbon dioxide interacts with water and what could be the consequences. So, carbon dioxide can combine with water. When combining with water, we have the production of a molecule that we call carbonic acid. Carbonic acid, as its name indicates, it's an acid. That acid is going to split, releasing a bicarbonate ion and a hydroxide ion. That hydroxide ion is going to cause water to be acidic. Maybe you've heard of acid precipitation, right? Or acid rains that cause the destructions of many forms of life, including forest, right? Trees. But in the aquatic environment, we also notice an increase in the acidity in oceans and seas. As consequence of that increase in the acidity, we also notice a decrease of carbonate. Carbonate, it's a chemical that is important for the structure of the exoskeleton of many invertebrates, including crabs, and you see the picture of a crab here, lobsters, clams, shrimps, to name only this. Now, when there is a decrease in carbonate, what happens is that the shell of this organism or these organisms become soft. And as they become soft, these organisms become very vulnerable to predators and to elements in the environment. So that's a pretty much of a bad news, right? We know this because we've studied the chemistry of life. So in this chapter, we are going to just dive into the chemistry of life. When we look at a living organism, such as a human being, the body of a human occupies space and contains a certain mass. That property of being made up of a mass, and we can quantify the amount of matter in a human organism and the volume that that matter occupies, we say that we are made up of matter. And matter itself, it's all the elements that make us up, right? So these elements occur naturally in the environment. There are about 92 naturally occurring elements on Earth in our environment. However, only some are found in large amount in living systems, such as you. Now, what are these elements that are found in large amount? When we consider our body, oxygen, for instance, account for 65% of all the elements that are found in a human. Carbon account for 18%. Then we have hydrogen that accounts for 10%, and nitrogen that account for 3%. So when we look at this four element compared to all other elements that are found making up our body, not only us, but also all other living organisms, we notice that this four element, carbon, oxygen, hydrogen, nitrogen, are by far the most abundant elements that are found in our body in living systems. With that being said, there are also many other elements that are represented in living organisms, including what we call micro elements. The micro elements are the elements that are present in small amount, including, for instance, calcium, phosphorus, sulfur, and then we have other elements that are not only present in small amount, but they are actually present in minute amount, extremely small amount. These are trace elements, right? These trace elements include, for instance, zinc, cobalt, lead, and many other elements, such as copper, right? Now, these elements are made up of building blocks that are called atoms. What is the structure of atoms? Atoms have a central component. That central component, it's called the nucleus. That nucleus is made up of two structures. One is a structure that is electrically charged positively. These are protons. The second structure that make up the nucleus of an atom, it's a neutron. A neutron, it's a subatomic particle that does not carry an electrical charge. Now, around the nucleus are going to gravitate electrons. These electrons are subatomic particles that are charged negatively, right? These electrons are going to orbit around the nucleus. Now, when we consider an atom, such as an atom of carbon, that atom of carbon is going to have a number of things we are going to draw or write associated with that atom. The first thing I want to attract your attention upon is the symbol. The symbol of an atom represents a short writing of that atom. A symbol for carbon, it's going to be C. A symbol for oxygen is going to be O. A symbol for sodium, it's going to be Na. Right? Then, in addition to the symbol of an atom, we are going to have what we call the atomic number. The atomic number is always written at the top of the atom, atomic symbol. That number for carbon is 6. The atomic number also represents the number of proton in an atom. Let me repeat that. The atomic number also represents the number of protons that make up a given atom, right? And then we are going to have a second number. That number, it's the atomic mass written at the bottom. The atomic mass for carbon, it's 1201. That atomic mass, it's actually the mass of the protons that make up the carbon atom and the mass of neutrons that make up that carbon atom, right? Now, you see that we have 6 protons. If we take out of 1201, which is the atomic mass, we are going to have 6, right? 601. Now, that 601 represents the mass of the neutrons, right? So, again, the mass of an atom, or the atomic mass, is the mass of the proton plus the mass of the neutrons. So that knowing the mass of these two subatomic particles, we can determine the atomic mass. Now, you notice that in the atomic mass, we only take into account protons and neutrons. We don't take into account electrons. Why? In spite of the fact that electrons are very much a structural part of an atom. The reason why electrons do not account in the mass of an atom, it's simply because electrons are simply too light, right? They have a neglectable mass. It's, for instance, in a real world and taking things to you, right? It's, for instance, trying to justify your mass by taking into account your hair, okay? How much is your hair accounting for your overall mass? Not much. How much is your eyebrows? How much are your eyebrows counting for the mass of your body? Not much, right? So this is also how much electrons account for mass in an atom. Now, we organize elements in a table that we call the periodic table. Now, because of the purpose of this course, I'm not going to dive into the periodic table, but know that on this particular periodic table, there are a number of elements that are represented here that are found abundantly in living systems, including hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur. They are all represented in red. But you also have many other elements here, including aluminum, chloride, fluorine. What else can I mention? Magnesium, sodium, potassium, calcium, to name only these few elements. Now, elements that we find in nature, such as, for instance, carbon, can occur, not always, can occur in multiple forms. We notice, for instance, that carbon occur in 3 forms. A form that we call carbon 12, another form that we call carbon 13, and a third form that we call carbon 14. Now, 12, 13, and 14 represent the atomic mass of each of this carbon. Then we can wonder, wait a minute. So the carbon element, it occurs in 3 different forms based on the atomic mass. Now, if the atomic number is exactly the same for these different forms of carbon, how come the atomic mass is different? Well, the atomic mass is different because sometimes for the same atomic number, we can have some atoms that have extra neutrons or less neutrons. For instance, in a case of carbon atom here, if we were to actually consider how many electrons are in carbon 12, we are going to, let me change the color here. We are going to say that in carbon 12, we have 6 electrons and 6 protons. So 6 electrons and 6 protons. While in terms of number of neutrons, we have 6 neutrons. So together, protons and neutrons, this is 12. But for carbon 13, the story is going to be different. We still have 6 electrons, 6 protons, but we have 7 neutrons. 6 plus 7 is 13. By the same token here, for carbon 14, we have 6 electrons, 6 protons, but 8 neutrons. 6 plus 8, that's 14. That explains why we have carbon 12, carbon 13, and carbon 14. These 3 forms of the same element are called isotopes. Isotopes occur in many kinds for a given element, right? Not all elements, but some that we know very well of, including carbon, iodine, to name only these 2. Now, these elements that are sometimes isotopic elements can actually, some of them, the isotopes, can decay. When they decay over time, they release energy. That energy sometimes can cause disturbances, right? These disturbances, we know them to happen. These are radioactive isotopes. So radioactive isotopes. Now, these radioactive isotopes, for carbon, for instance, it's carbon-14. Carbon-14 is radioactive because it releases energy, it decays over time. Now, with that being said, these isotopes are sometimes used in many aspects when we study biological systems, including in medicine, right? So that today we have what we call nuclear medicine. In nuclear medicine, we can use isotopes for diagnosis. For instance, we can actually give a patient a substance, for instance, a sugar, that carries one of the isotopes that is going to emit some energy. That energy is going to be captured by a scanner so that we can see in the body what particular area of the body is actively absorbing that isotope, right? So that today we can use a technology that we call positron emission tomography to scan some organs in our system, including our brain, some glands such as the thyroid glands, and many other organs in our system. Nowadays, we can, by providing extremely low doses of radioactive isotopes that are incorporated to glucose, for instance, so the patient comes in, we give him a solution of glucose containing a minute amount of radioactive isotope. Now we can actually run diagnosis for tumors, Alzheimer, epilepsy, even strokes, right? So by doing this, we can actually follow which area of the body or a particular organ is interacting with the isotope element, and we can also follow the patient over a certain period of time, over many years, to see if the condition is evolving over time or not. So you see that getting to know the chemicals and the role they play in living systems is very relevant for us, including obviously in nuclear medicine, but also in our laboratories. We use radioactive for many purposes, including sequencing, running chemical reactions to see the outcome when you start with some reactants. What are the products that we obtain, right? So we can do so many things. That's the bottom line, that are beneficial to us, human and living systems as a whole. All right. Isotopes can be used for many purposes, including the elimination of potential pathogens, right? So we can kill microorganisms with radioactive elements, right? How do they do this? By damaging DNA. By damaging DNA, the damages are so much beyond repair that the cell end up dying, right? We can also use radioactivity to treat cancers by targeting very specifically cancer cells. But radioactive elements can also be a bad news in the midst of trying to make it useful to us. Nuclear energy, it's very much a source of energy that we use extensively in the United States and many other developed nations to produce electricity and obtain energy that is going to allow us to achieve a lot of different things that improve our lives, right? However, when there are accidents around nuclear energy, that can be a major issue, right? Here we have the Fukushima facility in Japan that underwent a major accident because of the tsunami that occurred, if my memory is good, in 2011, but don't quote me on that. I don't remember quite. There was another major nuclear reactor accident that happened in Chernobyl, right? This is in Ukraine many years ago. I mean, long time ago. But this ended up actually causing major issues for the environment, but also for us, because people who live by nuclear plants typically are going to have chances to develop a cancer that are much higher than people who do not live near nuclear reactors or nuclear facilities.